Hi class, this is Dr. McGonigal with another Research Methods 2 lecture for you. Today we are going to talk about mean differences, specifically testing mean differences using SPSS. In previous videos we have covered inferential statistics, descriptive statistics, and data cleaning. If you have not already watched those videos, I suggest that you stop this video and watch those before you watch this video. In this video, we are going to learn how to conduct and interpret tests of mean differences using SPSS. This includes t-tests, both independent samples t-tests and paired samples t-tests, as well as ANOVA, specifically one-way ANOVA. As a reminder, make sure that you have also read the Price Chapter 13. In terms of our stages of data analysis, today we are wrapping up stage 4, your inferential statistics, in terms of your hypothesis testing about differences between groups in mean levels. This was gone over in detail in your inferential statistics video. I have it up here just to point out where we are today. So, these are the guidelines that you follow when you have two variables and you want to know which statistical test to use. If you have a nominal, independent, or predictor variable with either two groups or levels or three or more groups per level or levels, and a quantitative dependent variable or outcome, then you will use a t-test or an ANOVA, which we'll cover today. As a reminder, you're going to use your composite variables for your outcome variables when you're doing this. So remember that your composite variables are the average of the different items that are included in your particular measure. We went over in detail how to create composite variables in your data cleaning video. In terms of deciding which test of mean difference that you want to use, you first want to ask how many levels does your predictor have. For instance, if I am looking at pet ownership and I have a variable that is 0, meaning no pets, and 1, meaning one or more pets, then I have 2 levels. So in that case, I want to ask, am I testing the same subjects at different time points or occasions? Or am I looking at different subjects and comparing them to one another? If I am looking at the same subjects over different time points or administrations, then I will use a paired samples t-test. If I am looking at different subjects and comparing them to one another, then I will be using an independent samples t-test. If my independent variable or predictor has more than 2 levels, then I will use a one-way ANOVA. For example, if I wanted to test the average income based on college major, and I had 5 different college majors that I was comparing, maybe I looked at psychology, engineering, computer science, management, and English. So I had all of those. In that case, I clearly have more than 2 levels of my predictor variable. I have more than 2 groups. Therefore, I need to use a one-way ANOVA. Let's look at an example. This is kind of a silly example and not a hypothesis that has a basis in research, but it will help us illustrate what we're doing here. This hypothesis is that people who own pets will have greater levels of self-efficacy than people who do not own pets. Again, this is not something that is based in any scientific literature. It's just a funny example for us to use to show you how to use SPSS to run your t-test. In this case, we first need to determine what is the test that we're using. So first, what is our predictor variable? Well, that's pet ownership status. So either yes, at least 1 pet, or no pets. Is the predictor categorical nominal or quantitative? Well, it's categorical nominal. And how many levels does it have? It has 2 levels. Either yes, I own at least 1 pet, or no, I do not own a pet. The outcome variable is self-efficacy, and this is a quantitative variable. We have measured it on a scale from 1 to 5. What is the correct statistical test for a nominal predictor and a quantitative outcome? In our case, because we have a nominal predictor with two groups in a quantitative outcome, therefore we are using an independent samples t-test. In other words, we're comparing two groups, those who own pets and those who do not own pets. And we're looking for mean differences in our outcome, which is self-efficacy, by that group. In other words, we're looking for differences in self-efficacy between people who own pets and people who do not own pets, such that people who own pets have significantly higher mean levels than people who do not own pets. In SPSS, to conduct this analysis, again, we would want to make sure that we have first calculated our composite variable or created our composite variable for self-efficacy. After we have our composite variable created for self-efficacy, we go into Analyze, we select Compare Means, and then we select Independent Samples t-test. When you do that, you will see a screen pop up that looks like this. Now, we can take variables that are in this left-hand column and we can move them over to the right-hand side. The first thing that we want to do is find our outcome variable. So our outcome variable goes into the test variable box. In this case, our outcome variable, our quantitative outcome variable, is self-efficacy. So I have moved that over here. The next step is to find your nominal predictor variable and enter it under grouping variable. So the group variable, the nominal variable that I'm using here is pet status, either 0 for no pets or 1 for pets. After I have entered pet into grouping variable, I need to enter the coded values for the groups here. So I click Define Groups, and a little box will pop up that has place for me to type 0 and 1 to indicate that those are the two levels that exist in my pet variable. Then I can click either Paste or OK. Paste will create your syntax file that you can then run, or you can just click OK to get your output file. And this is what your output file looks like. So you have first here something called group statistics. And you can see here that you have no pet or at least one pet. Those are your two groups. And you are provided with the mean and the standard deviation of people who have no pet and people who have at least one pet. So we're just going to look at that for now and not interpret it quite yet, because we need to next go in to see whether our results were statistically significant. So we move on into our independent samples t-test output. The first thing that I'm going to look at here is my significance level. So we can see that the statistical significance is 0.81. So remember that we're always rounding to 2 decimal places. 0.81 is greater than 0.05. So I do not have support for my hypothesis in this case. I am not rejecting the null hypothesis because my p-value is greater than 0.05. So I next look at my t-statistic, which is here, it's 0.250, and my degrees of freedom, because I am going to need to include those in my write-up. So now I'm going to come back to these means, and I know that the difference between them is not statistically significant. And so that tells me that I can look at the difference here between these. People who had at least one pet had a 3.00. People who had no pets had 3.20. But that difference is not meaningful. It's not statistically significant. So here is the example of how I would write this up in a paper. Again, remember that the hypothesis was that people who own pets will have greater levels of self-efficacy than people who do not own pets. The results from an independent samples t-test showed no statistically significant difference in self-efficacy based on pet ownership. Then I have an italicized lowercase t indicating that I've used the t-test, parentheses 8 for my degrees of freedom, equals 0.25. Okay, so let's look back at our output to see where that comes from. The t is here, and the t is here, and the p-value is 0.81. So again, I'm going to look here and see that my p-value is 0.81. So that's where that all comes from. Remember that you're italicizing your statistics, your letters that are denoting your statistics. So a T here and the P here are both italicized. And I mentioned this also in your correlation video, but according to APA style, you report exact p-values, not just p is less than 0.05 or p is greater than 0.05. So I have p equals 0.81 here. I go on to say that those with at least one PET, and then I provide the mean and the standard deviation for self-efficacy for those who have at least one PET, have similar levels of self-efficacy as those with no PETs, and I provide the mean and standard deviation for those with no PETs. Therefore, our hypothesis was not supported. Okay, so moving on, let's talk about a paired samples t-test. Now remember that we use the paired samples t-test when we are comparing the same individuals over two occasions or two time points. For example, we might have a hypothesis that individual scores on a math test will significantly increase from time 1 to time 2. Perhaps we think that because they had exposure to the math test, they had time to practice, that their scores would increase between time 1 and time 2. In this case, you are not comparing one group of people to another group of people, like we just did with pets, people who had pets versus people who have no pets. Instead, we are comparing one time point to another, time 1 versus time 2, for the same people. This is a nominal predictor, your time 1 and time 2, and you have a quantitative outcome, which is test score. So you know you want to use some form of a t-test, and in fact, we use what is called a paired samples t-test. In order to run a paired samples t-test using SPSS, we would first again make sure that if we have any composite variables to create, that those are created correctly. Then we go into Analyze, we click Compare Means, and we click Paired Samples t-test. On the next screen that comes up, you will move the variables of interest from the left side of the screen into the right side of the screen. So you want to put the variables together within a pair. So pair 1 is our score on variable 1, our score on test 1 under variable 1, and our score on test 2 under variable 2. So these two are paired. This is the paired test that they are conducting. Then we can paste into our syntax file and click Run, or we can click OK. This is the output that comes out when you run that particular paired sample t-test. So again, the first box will have our descriptive statistics, our means, and also our standard deviations, which are over here. They're not in a box, but those are also important to report as well. And then what we do first is we come down here to the third box where it says Paired Samples Test, and we look at three boxes here. We have our t-value, we have our degrees of freedom, and we have our statistical significance. So looking at the statistical significance, that's 0.000. So that's clearly less than 0.05. So this is a statistically significant result. We take note that our degrees of freedom are 9, and our t is negative 7.01. Now let's take a look at the means. Now that we know that it is a significant difference, we can look to see whether the direction of our results is consistent with what we hypothesized. So remember that we hypothesized that test score at time 2 would be higher than test score at time 1. And indeed, we see that that is the case. So our test score at time 2, the average is 85.7, compared to the test score at time 1, which is 72.1. So let's look at how we would report this. Remember that our hypothesis is that individual scores on a math test will significantly increase from time 1 to time 2. Our reporting would be, the results from a paired samples t-test showed a statistically significant increase in test score. Lowercase italicized t, 9, remember that's our degrees of freedom that we got from the previous slide, equals negative 7.01, that's our t value. P, italicized p, is less than 0.001. Now you might be wondering, why am I using less than 0.001 when APA style wants you to report exact p-values? Well, let's take a look here. The significance is provided at 0.000. Well, in reality, we could probably go on for a few more decimal places. It wouldn't be exactly 0, it would be something else besides 0. So rather than saying it is 0, because in reality it's probably not 0, when we have something that is less than 0.001, we use this. We just say p is less than 0.001. We go on to say that scores at time 2, and we provide the mean and the standard deviation for scores at time 2. We're significantly higher than scores at time 1, and we provide the mean and the standard deviation at time 1. Therefore, our hypothesis was supported. Let's move on to talk about testing for mean differences when you have more than 2 groups of individuals. For instance, we have another kind of silly hypothesis here that has no basis in research, but is one way that we can illustrate how to run an ANOVA. So this silly hypothesis is that people who own cats will have higher self-efficacy than people who own dogs and people who do not own any pets. So what is our predictor variable here? Our predictor variable is pet status, either cat, dog, or no pet. So our predictor variable, being pet status, cat, dog, or no pet, is clearly categorical or nominal in nature. How many levels does this variable have? Well, it has 3 levels, right? Because it's either cat, dog, or no pet. The outcome variable is self-efficacy, and our outcome variable is quantitative because it was measured on a 5-point Likert type scale. And what is the correct statistical test for a nominal predictor with these 3 levels and a quantitative outcome? The correct answer is that it is an ANOVA. We look for mean differences in an outcome by group. So in other words, we're looking for differences in self-efficacy between cat owners on the one hand and dog owners and those with no pets on the other hand. And specifically, we're looking to see whether cat owners' self-efficacy levels are significantly higher than those who own dogs and those with no pets. In order to run a one-way ANOVA in SPSS, you click on Analyze, Compare Means, and One-Way ANOVA. Then you move your quantitative outcome variable over to the right side under your dependent list. So your variables are all listed here on the left. You click to move it over to the right to your dependent list. As a reminder, you want to make sure that you're creating your composite variables before you're running this analysis and that you're using your composite variable as your dependent variable. The next step is to move your nominal variable over into the box called factor. In this case, I have created a new variable in our demo dataset called pet type. And I have said 1 is cats, 2 is dogs, and 3 is no pets. So there are a few other steps that I need to conduct here before I can click to paste my syntax or to click the OK button. The first is that I need to click post hoc. So see this button here, post hoc? This pops up and we check Bonferroni and we click continue. Then we click on options, which is this one here, and we click descriptive so that we get descriptive statistics. Then we click continue, and at this point now we can click either OK to run the analysis and get our output, or we can click paste and create a syntax file where we run our syntax that way. here's the output that you get when you run a one-way ANOVA. So the first box at the top, again, will give you your descriptive statistics. In this case, we can see that 6 people owned no pet, 6 people owned a cat, and 8 people owned a dog. And we have our means and our standard deviations for each of those groups. Just looking quickly at it, we can clearly see that cat owners have higher levels of self-efficacy, 4.67 compared to people with no pet or to people who have a dog. We still don't know if that's statistically significant, so we need to continue on. In the next box, we have our degrees of freedom, which we need for our reporting. We have our F statistic, which is our test statistic, similar to how you have an R or a T, an R for correlation test or a T for a t-test. And we have our significance level. In this case, our statistical significance is 0.000. Again, that's clearly less than 0.05. So we do have support for our hypothesis so far. Now, as you'll see, we need to do a few more things before we can determine whether a hypothesis was fully supported, but this gives us confidence to at least continue looking. The next box here, we have multiple comparisons. And why do we need something called multiple comparisons when we have an ANOVA as opposed to a t-test? Well, if you remember, when we have an ANOVA, we have 3 or more groups. That means that we're comparing group 1 to group 2, but we're also comparing group 1 to group 3 and group 2 to group 3. So we need to see the results of each of those different comparisons to determine whether or not our hypothesis was supported. So remember that our hypothesis was that cat owners would have higher self-efficacy than dog owners and people with no pets. So let's take a look at cat under pet type. We're going to cat, that's the second one. And we can see here, this is comparing cat to no pet and cat to dog. So if we look at cat compared to no pet, indeed we do have statistical significance there. And if we compare cat to dog, we also have statistical significance there. So based on the fact that we have statistically significant results overall, plus we have significant results when we compare cats to no pets and cats to dogs, and we can look up here at the means and we see that cat owners have a higher level of self-efficacy than dog owners and people with no pets. All of that put together tells us that our hypothesis is supported. So remember that our hypothesis is that people who own cats will have higher self-efficacy than people who own dogs and people who do not own any pets. This is how you would report the results in a paper. The ANOVA results showed a statistically significant F test, and then you have your F, which is uppercase and italicized, 2,17, which you get from your degrees of freedom here, equals 68.90, 68.90. P is less than 0.001. That's what you get from here. Similar to the last one we went over, when it's 0.000 like that, we report as less than 0.001. Then we say results of multiple comparisons indicated that, as hypothesized, cat owners, and we provide the mean and the standard deviation, and I got that from here, 4.67, standard deviation is 0.52, had significantly higher levels of self-efficacy than dog owners, mean of 2.75, standard deviation of 0.46. So 2.75 for dog owners, standard deviation 0.46. And those who do not own a pet, mean of 2.00, standard deviation 0.00. Mean for no pets is 2.0, standard deviation 0.00. Though not hypothesized, dog owners also had significantly higher levels of self-efficacy than those who did not own a pet. So you can probably see that we have more information here in our multiple comparisons than we needed based on what we had hypothesized. So we don't have to report that extra information, but I usually do for the sake of completeness. So we can see that dog owners had higher levels of self-efficacy than those who did not own a pet. So if we look at dog owners and compared to no pet, they are also statistically significant. The p-value is 0.01, which is less than 0.05. So to wrap up, you should now know how to conduct an independent samples t-test in SPSS, interpret and write up the results, conduct a paired samples t-test in SPSS and interpret and write up those results, and conduct a one-way ANOVA in SPSS and interpret and write up those results.